The future. Ever wonder what it's going to be like 20, 30, or even 40 years from now? Hello, and welcome to Futurepath. I'm Americo Forestieri, Director of External Affairs at the NASA Lewis Research Center in Cleveland, Ohio. In the future, we all know our clothes will change, our hairstyles will change, and even the music we listen to will change. But how will the technology that's being developed today affect our lifestyles in the future? For a long time, NASA's been concerned with developing aircraft that will fly further, higher, and faster. But more recently, our concern has changed to flying aircraft with greater fuel efficiency and protecting our air quality. NASA's developing a propulsion system which involves both the jet engine and advanced propellers. It's called the Advanced Turboprop System, and it's shown here. The Advanced Turboprop project combines the efficiency of the propeller with the power of the turbine. This technology base provides for the future development of the single rotation and counter rotation turboprop propulsion systems. The idea is to reduce fuel consumption in both military and commercial aircraft. The initial concept for the advanced turboprop system first came about in the mid-1970s due to the OPEC oil embargo and the sharp rise in fuel prices. The fuel burned in a 727 or 737 jet aircraft can be reduced by as much as 50% with a propeller-driven aircraft. Advanced turboprop propellers are very different from traditional propeller designs. They are very highly swept and very thin. There are 8 to 10 blades rather than the 3 or 4 blades that we are used to seeing. We therefore get more power in a smaller diameter. It allows us to fly faster, up to 600 miles per hour, and at a much higher altitude, around 35,000 feet. The noise levels of this new turboprop are much less than the traditional propeller or turboprop aircraft. There have been 3 series of flight tests in the Advanced Turboprop project. 1, the NASA GE Boeing flight tests of the counter-rotating unducted fan on a B-727 aircraft. 2, the NASA Lockheed prop fan tests of a single rotation advanced turboprop on a Gulfstream II aircraft. And 3, the GE McDonnell Douglas tests on an MD-80 aircraft. These tests verified the readiness of the Advanced Turboprop project for commercial engine development. Another way NASA is helping the aviation industry to a more efficient future. Another form of a propulsion system is the diesel engine.
When you think of diesel engines, you probably think of certain types of cars or heavy trucks barreling down the highway. But technology developed by NASA is currently creating breakthroughs in aircraft diesel engines. NASA is also designing remarkable improvements for diesel engines in trucks. Enthusiasm for the development of diesel engines is reaching pre-World War II levels. That's when diesel engine technology was very popular for its endurance and altitude records set on long-distance flights. Although the war halted further development of aircraft diesel engines, work on the engines continued again well after the war. The United States Army is developing and designing diesel engines for helicopters. Various industries throughout the world are planning to develop aircraft diesel, and diesel engines used in heavy-duty trucks are being improved upon by the Department of Energy. Diesel engines are primarily used when high power is needed and fuel consumption and durability are of concern. Trucks, stationary power plants, large ships, even tugboats use diesel engines. A man who sees a bright future in diesel technology is Mr. William Wintucky. Mr. Wintucky, who has done much research on aviation diesel, is involved with a number of projects at NASA Lewis Research Center aimed at improving diesel engines. Joint research is underway involving NASA and the Department of Energy to make diesel engines more fuel efficient. Technology to redirect fuel exhaust back into the engine could result in reduced fuel consumption of long-haul trucks by up to 30%. Mr. Wintucky explains the difference between diesel engines and gasoline engines.
A diesel engine is basically the same as a gasoline engine, except for the combustion process. And the difference in the combustion process is that as the fuel is compressed by the piston, the temperature is raised to a point where ignition is started by the heat of compression. from the piston. In the gasoline engine, the combustion is controlled by a spark plug, and ignition is controlled when you want it started by an electrical impulse which discharges through the spark plug. In the case of the diesel engine, when the fuel is raised to its auto-ignition temperature, the fuel ignites throughout the combustion chamber at the same time, and therefore the pressure rises very rapidly, just like an explosion, and as a matter of fact is an explosion. And that's why sometimes when you hear a diesel engine going down the street and it sounds like it's knocking, you are actually hearing the explosions of the combustion process. Because of the explosions or very rapid pressure rises in the diesel combustion chamber, the walls of the chamber have to be thicker, and also the bearings have to be larger. And overall, the engine must be much stronger to design for the explosions.
Why develop better diesel engines, and why create one for aircraft? Diesel fuel, which is oil, can be produced from a wide variety of sources, such as, of all things, sunflower oil or peanut oil. Also, diesel fuel is safer because it does not ignite on its own. Absence of an electrical ignition system eliminated radio interference, another safety factor for aircraft diesels. The desire to use the fuel-efficient diesel engine in aircraft is not new.
Interest in aircraft diesel engines goes back almost as far as internal combustion engine gasoline engines, dating back to 1911. The main reason that diesel engines were considered for aircraft use very early on was, at that time, all of the gasoline engines were carbureted. And one of the main problems that aircraft had was icing. And with diesel fuel, since the fuel was injected directly into the cylinder, there was no problem with carburetor icing, or ice forming in the carburetor, stopping the fuel flow and, of course, stopping the engine. A second and almost important reason was the fact that diesel fuel does not auto-ignite, which was a problem in the early days of aircraft. Auto-ignition is the process where the fuel ignites spontaneously or without any external source. In the case of gasoline, gasoline vaporizes very easily, and the vapors are very combustible. With diesel fuel does not vaporize very easily and stays as a liquid, so therefore it is a much safer fuel to use.
The diesel, or compression ignition engine, was first designed by Dr. Rudolf Diesel of Germany. By 1897, the first commercially practical diesel was put into use in the form of an industrial engine. About 1910, the heavy, slow-speed diesel engines were replaced with higher-speed, lightweight engines, which provided a major step toward aviation diesel use. In 1931, the 9-cylinder Packard diesel, built in the U.S., set and still holds the world diesel flight endurance record of 84 hours and 35 minutes without refueling. Credit for originating the diesel aircraft engine is given to Germany's Dr. Hugo Junkers.
Dr. Junkers was interested in development of a diesel engine to power commercial aircraft. At the time, there were no transatlantic flights because gasoline-powered aircraft could not carry enough fuel to cross the Atlantic and still have enough room left for payload. And the diesel engine was the only engine at that time known to have the fuel efficiency that would allow transatlantic flight and still have room to carry either mail or payload. So in conjunction with Lufthansa, the Junkers-Jumo engine was developed and installed on a number of flying boats which Lufthansa entered into transatlantic service from the Azores to South America in 1936.
The Jumo continued operating until the outbreak of World War II, when production turned to the more easily designed and constructed gasoline engines from military aircraft. The British developed the last major aircraft diesel engine, which used a turbine to give it more power. Mr. Wintucky gives us some insight into the most fuel-efficient engine ever flown.
British Napier Nomad engine was very unique. It was really a very high-performance turbocharger in that the exhaust gases from the engine, the diesel portion, were ducted into a fan-like turbine, which then drove the compressor, which compressed air and put it into the inlet of the diesel engine. This raised the overall pressure in the engine and allowed it to produce more power for the given size of engine that it was. And in many cases, engines will produce 2, 3, and even 4 times as much power when turbocharged versus when they just have a carburetor on them, as would be in your normal automobile engine.
Turbocharged diesel engines for aircraft are making a comeback. NASA research has inspired the U.S. Army to develop the technology to use diesel engines in helicopters.
Early in the 1980s, the Army did a number of studies in looking at engines for light helicopter use. And they found that through the use of a very highly turbocharged diesel engine, they could get an increase of up to 50% in range or a payload that a helicopter could carry. And since for the Army, fuel represents up to 70% of the amount of supplies that has to be transported to the battlefield, a 50% savings in fuel or a 50% increase in payload represents a tremendous savings to the Army and a reduction in a logistics problem. So the Army was very much interested in the use of the diesel engine to lower part of its fuel requirements. The Army really took the expertise that NASA had developed during the time that it was looking at the aircraft diesel engine and is now using this expertise in its own program.
The engine being developed by the Army for helicopters is expected to be operating by the mid-1990s. And work is being done to develop materials and lubricants able to withstand the high temperatures, high speed, and high pressure of an aircraft diesel engine.
The oil that you use in your car runs at the most about 350 degrees Fahrenheit, whereas in the engine for the helicopter, we're talking about running as high as 800 degrees Fahrenheit. There is no oil now commercially available that will withstand these temperatures. There are lubricants that can operate at these temperatures, but they cost thousands of dollars. And the goal of our program is to develop new lubricants that will be economically feasible and operate within the temperature limitations that are required to produce the power for this engine.
It is hoped the United States Army's efforts with diesel technology will result in a safer, more fuel-efficient and economical helicopter fleet. The diesel engine's low fuel consumption feature is valuable to countries such as Italy and Japan, where fuel is very costly, and also to the USSR, where long-range flights abound. Decades ago, scientists were able to see the promise of diesel engines in aircraft. The previous work is the firm foundation on which today's research can stand. Research that NASA and people such as Mr. Wintucky believe is important and could result in 21st century aircraft diesel engines.
Now let's talk about another engine you've probably never even heard of, the Stirling engine.
As part of the work being done in today's dynamic aerospace industry, NASA Lewis Research Center is further developing a rather remarkable engine, which was invented, surprisingly, way back in 1816. Named after Robert Stirling, its inventor, the Stirling engine very well could be the most exciting and efficient new type of energy conversion device in space within the foreseeable future. Already, the engine has been developed and tested successfully as an automotive engine, using less fuel than the car engines we use now. And the Stirling engine can use a variety of fuels: gasoline, diesel fuel, alcohol, kerosene, and others. During this report, though, we will explore this fascinating engine and its possible uses in space. Logically, we begin by asking, how does the Stirling engine work? Simply put, the engine works because of a difference in temperature. One end is kept hot, while the other is cold. Within the engine, a displacer piston moves gas from the hot end to the cold end, and back again. As that gas moves, its pressure changes. When the pressure is high, the gas pushes against a power piston, causing an output of energy. Since the heat input is supplied externally, anything that will burn or make heat, such as solar or nuclear power, fossil or gaseous fuels, or even garbage, will make the Stirling engine run. NASA is working to develop materials that can withstand extremely high temperatures to be used in the construction of the Stirling engine. There are two kinds of Stirling engines, the kinematic and the free piston. The free piston shows the most promise as a source of electric power in space. This concept is relatively new, approximately 25 years old. In their basic form, both types have a piston and a displacer. In the kinematic engine, the piston and displacer are connected to other parts of the engine. But in the free piston, the piston and displacer are not physically connected to anything and move solely by forces and pressures within the engine. At NASA's Stirling Engine Project Office, Jim Dudenhofer, Special Project Manager, had this to say about the Stirling's suitability for use in space.
So we have gas bearings to eliminate friction and wear. We have a totally hermetically sealed unit which helps us with gas leakage and permeation in the long term. Bear in mind, we're talking about an engine, when we talk about space, that must live out there without a mechanic for anywhere from 7 to 20 years. And so long life and good maintainability are essential for a space power engine.
NASA Lewis Research Center continues its work with the Stirling engine as part of a project called the Civil Space Technology Initiative. The purpose is to develop various technologies for future use in space. Until about 1985, there were free piston Stirling machines that could generate only a maximum of 3 kilowatts of electricity. NASA, in trying to increase power output, developed, with Mechanical Technology Incorporated, a 25 kilowatt electric machine. Now, NASA is trying to find out how much larger Stirling engines can be made. Initial studies indicate power levels as high as 500 kilowatts per machine, and possibly even higher. And finally, why develop the Stirling engine now, when already power has been generated in space in other ways for years? Jim Dudenhofer answers.
Space technology is growing by leaps and bounds, and instead of needing hundreds of watts in space, we're on the threshold of needing millions of watts. If we're going to colonize Mars, if we're going to colonize the moon, if we're going to manufacture in space, we need tremendous amounts of electrical power. Photovoltaics simply become too large. The great big solar panels that we're all accustomed to seeing simply become too large. They're too difficult to move. They have some limitations in polar orbits because of the problems encountered with the Van Allen radiation belts. Solar dynamic machines, of which Stirling is one, can operate any place that there is a source of heat, be it the sun, be it nuclear. A Stirling engine, once it's supplied heat, can function. and it can produce large amounts of electrical power output in a relatively small and lightweight package. And that's our purpose for being involved in this type of technology development work.
The amazing Stirling engine, one of the most efficient heat engines made, and just one of the many technologies being developed today at NASA Lewis Research Center.
Now that we have a background on understanding how the Stirling engine works, let's view a short animated piece on the development of the Stirling engine for its use in space.
The free-piston Stirling engine effort is directed at high efficiency, long life, and a high specific power to meet NASA's needs for future space missions. The successful tests of the 25 kilowatt space power demonstrator engine at 650 degrees K in 1985 completed phase 1. Phase 2 of the three-phase Stirling program is now underway, leading to the design, fabrication, and testing of a 1050 degree Kelvin superalloy Stirling engine. This is one of several conceptual designs. The successful development of the 1050K experimental Stirling engine provides a low-cost basis for the low-risk future development of the Phase 3 refractory alloy 1300K engine. It will also provide a variable alternative power conversion system for an early flight demonstration of the SP-100 nuclear space power reactor. The performance objectives of a typical single-cylinder design are: alternator output, 25 kilowatts of electricity. Engine efficiency, 30%. Inlet temperature, 1050 degrees Kelvin. Outlet temperature, 525 degrees Kelvin. Working fluid, helium. Engine alternator frequency, 90 Hertz. Specific mass, 6.4 kilograms per kilowatt of electricity. Operational life, over 7 years. With lessons learned in the 650 Phase 1 engine program, the Super Alloy Phase 2 engine is being confidently designed for high performance and long life with current nickel-base super alloys. The free-piston Stirling engine achieves its high performance in part due to its simplicity of design and operation. Its major features are the heat exchanger assembly, which will have only 40 heater-cooler modules to significantly reduce the number of welded tube joints. The displacer, one of 3 moving parts, is a 5-kilogram piston floating on a film of helium and shuttles the working fluid from the hot expansion space to the cold compression space, and vice versa. The reciprocating action of the 12-kilogram power piston caused by the working fluid produces electrical power in the linear alternator. The 12-kilogram balance piston oscillates to fully counteract the combined vibrations of the displacer and power pistons. Alternate engine designs employ opposed sets of pistons, synchronized to eliminate the need for a balanced piston. Magnets in the power piston oscillate through the stator laminations to produce alternating current. The pressure-volume diagram shows the cyclic variation of pressure and volume in the working space between the power and displacer pistons. The area enclosed by this diagram is indicative of the engine's thermodynamic power. The following computer-generated animation shows relative motions of the 3 pistons. For clarity, their speeds have been greatly reduced from the normal 90 cycles per second operating frequency.
We hope you've enjoyed our program. I'm Americo Forestieri, hoping you'll walk with me again along the Futurepath at the NASA Lewis Research Center in Cleveland, Ohio.
rate is now 70 feet per second. Gear her down.